Hi, today we are looking into linear maps between vector spaces V and W. So you can also see it on the right hand side. We have two vector spaces V and W and a linear map between them. We call it phi here. And in particular we are interested into the kernel and the image of a given linear map phi. We will look into the definitions and also look at one example and determine the kernel and the map and the image for this example. So let's start with the image. So the image of phi is defined as phi on big V, which is nothing else than the whole set of images where we apply phi on V. Yeah, and we do this for all vectors V from the vector space big V. So you can also see it here. We have our vector space V, and these lines here on the outer describe that we apply phi on the whole vector space V and see what we can get actually inside the vector space W, which is marked here in green. So this can be 0 only, can only also be the whole vector space W. In this image you can see it's a strict subset of W and also bigger than 0. So for the kernel, of phi, it is defined as all vectors inside V where phi maps them to 0. Okay, so you can see it here on the left hand side. So this time it's a set inside our starting vector space V. It's a subset of V. Again, it can be even the whole vector space V or just 0. 0 is always contained, we can see this later. And in this image it's a strict subset of V and bigger than 0. And here, as you can see, we are looking into all elements of V which are mapped to 0 by our linear map phi. So this is the kernel. Both are subsets of V and W respectively, and they're even linear subspaces. So not only subsets but also even linear subspaces. We will prove this in a future video. So far, if this was interesting to you, please consider subscribing to this channel, like the video, leave a comment, and stay tuned for future proofs regarding linear maps, linear subspaces, kernels, and images. So now we will look into one example. And we are given a linear map FA from R2 to R2, where xy is sent to this matrix multiplied by the vector. So for the kernel, we are interested into all the x and y's such that the result is 0. Yeah, the 0 vector. So this is equivalent to 1, 0, 1. Then we're interested into x and y such that we get 0, 0 here. And from here we can read out, because of this upper triangular form, or here, or because of this upper triangular form, we can read y equals 0 because of this upper triangular form, and we can see that 1 times y equals 0. For this reason y must be 0. And then we can also read 2 times x plus y equals 0. This is the first line here, and this is equivalent to 2x equals 0 because y is 0, and this is equivalent to x equals 0. So this means kernel of FA is just 0. So regarding the image, it's useful to observe the following 2, 1, 0, 1 of x, y. So this is then 2x plus y and just y here. And this is the same as 2x and 0 plus y, y. And this can be further reformulated to 2, 0 times x plus 1, 1. So we can see that the image is the linear combination of 2, 0 and 1, 1, because x and y are arbitrary real numbers. So as the image can mostly be of dimension 2, because we are working here in R2, so the image cannot have a bigger dimension than 2. Yeah? The image is something part of our target vector space, and our target vector space here is R2. So the image can have mostly dimension 2. As you can see here, the image is composed of 2 linear independent vectors, 2, 0 and 1, 1. We can conclude that image of FA has dimension 2. And from this it follows image FA must be exactly R2. So, I hope this video was useful to you. Stay tuned for more content related to images, kernels, linear maps and matrices.